Today we're talking about object pools, which are an alternative to allocators, that is malloc and free, that allow you to avoid some of the fragmentation and non-determinism issues that come with malloc and free. Hey folks, welcome back and Happy New Year. I hope you're all doing well wherever you are. Today we are talking about memory allocation, and if you've been watching this channel for a while, you've probably heard me talk about how with embedded systems and other constrained devices, there are times where we like to avoid dynamic memory allocation, specifically malloc and free, because it can cause some problems with fragmentation or non-determinism, meaning that my program might not always run the same way, and this can be particularly problematic if I have a device with very little memory. If I use a little more memory this time or next time, I might get different behaviors and bugs that might only crop up, very rarely, and that can cause problems. So in those cases, what I'm looking for is code that always runs exactly the same. I want to also make guarantees about how big my heap can get. I don't want it to be able to just grow to whatever size it wants. And those are things that malloc and free don't necessarily do well for us. So today we're going to see what we can do about that. Also, I want to point out that often our first go-to in solving this problem is to just statically allocate something. If I need a variable, just make it global or use local variables, as long as I'm not, again, we can have problems if our stack grows too much, but static allocation is the easiest way to go. And so I want to emphasize that that is probably the first thing to go to if you're just like, I need a variable, I need it to always be there, I need to have guarantees, know exactly how much memory I'm using. That's probably where I'd start, but this can come with its own set of downsides, and so sometimes people are looking for a middle-of-the-road option, and that's what we're looking at today. Also, I want to mention, because somebody out there I'm sure is raising their hand going, oh, yeah, I know some allocators are designed to reduce fragmentation. This is true of slab allocators or the slub or slob. Anyway, there are a bunch of allocators that are out there that people have proposed that are designed to reduce the amount of fragmentation you get. Some of those are even used in mainstream operating systems. Please do let me know down in the comments if you'd like me to talk about those in a future video, but that's not what we're talking about today. Today we're talking about object pools, which present a simpler and I also think quite effective option as long as we are willing to accept a few limitations. And in order to look at those, let's jump into the code. Okay, so today we're going to start off with this really super simple program. All it's going to do is it's going to allocate using malloc. It's allocating 15 vector objects, and it's going to print out, basically it's going to say I got the vector, and it's going to print out the address where that vector is located. Sorry about this typo. Yes. Okay, so this code is basically just going to, simple for loop, it's going to allocate space. The size of it is for this vector3 object or struct, and then we're going to free that once we're done with it. Also, yes, this is C, which is not considered an object-oriented language, and I know I just referred to these as objects. They're technically structs. Yes, we are working in C, and terminology is going to get a little fuzzy here, but that is because when you get out there, people are not going to refer to this thing as a struct pool. They're going to call it object pool, and sometimes we call the things, when I call malloc to give me a block of memory, I'm often referring to this thing that I got back as an object, even if it is technically a struct. So yes, I'm sorry, I hope this doesn't confuse anyone, but the term object is used in a lot of different ways, and so I hope that's fine as you stick with me. But anyway, these objects, these vector3 structs, are defined up here. It's basically just, so this is not a vector in the C++ vector sense. This is a mathematical vector, a three-dimensional vector that has an X, Y, and a Z component. So yeah, math vector, not C++ data structure vector. Now the idea here is that whenever in my program that I want to use one of these vectors, maybe I'm doing some linear algebra and I need some space to store an intermediate value for a vector, I can just go ahead and allocate some space in memory, and then I can use that memory for a certain amount of time and then release it when I'm done. And yes, I recognize this example right here is not really doing much of anything. It's a little toy problem. I'm not doing anything with these objects. And yes, I could just allocate the variable locally. Like I could just say, instead of doing this, I could just make this a vector3v, and now I've got a local variable, which is a vector, and we could play with that. But today I want to talk about object pools, but I didn't want my example to be so complicated that it distracts from understanding how object pools work. So a real life example might be, let's say, a graphics application that is doing some 3D rendering, or maybe a physics simulation that's doing, again, some kind of 3D simulation of forces and movement and things like that. Or maybe it's a robot or a drone that's got an autopilot internally. You get a lot of vectors, used in those applications. And what can happen sometimes is rather than, right now I'm basically grabbing these vectors in one place, but let's say we had code that is using these vectors and trying to allocate them in maybe 100 different places or 50 different places during the code. So there's all sorts of different locations that need to use this very common data type. And let's say that these vectors sometimes have to be used outside of the scope of a single function. So local variables might not really be our friend. They're not really going to work for us. And we also don't want the non-determinism and fragmentation that would come with malloc. And then let's also say that I'm really constrained on memory and I don't want to have 100 different global instances of this. I don't want to have a ton of global variables. I don't want to declare 100 different global vectors just because at some point I'm going to need to use all of them. For me, this is relevant because I'm often working with microcontrollers that only have a few K of RAM. And so how much memory I'm using at any given time can be an issue. And of course, there is a chance that I may need to store 100 active vectors at a given time, in which case you got to find space. You got to find somewhere to store that in memory. But often that's not the case. Let's say that yes, there's 100 places in my code that need to use vectors, but at any given time, I never need more than, let's say, 10 of those at once. And so we can share the same memory. Different pieces of code can share the same memory. That's where an object pool is going to be useful. So just to get started, let's look at how we do this. Let's start with something like this. Let's come up here and let's just say, I am going to define the number of objects in my object pool. Because the idea, what we're going to try to do here is we are going to say, I'm going to statically allocate a set of objects, right? A set of these vectors, these things that we want to share. And then I'm going to allow different pieces of code to basically borrow one when they need it and then put it back when they're done. This is kind of like what malloc and free are doing, but it's slightly more constrained because all of the objects are the same type and the same size. So we can define the size. Basically, let's say we're going with 10 objects. I can change this later if I want. And then let's also come down here and say, I'm going to make an object pool, which is just going to be an array of num objects. And then let's just zero everything out. We'll just initialize it like this. Okay, and just to keep things, I know I put this constant up here. I'm going to move it down because I like the idea of keeping my object pool all together. And it needs to go down here because it needs to come after the definition of vector 3. Okay, so we have our object pool here. That's great. And then we're going to need to declare two helper functions. Okay, so, and you can call these whatever you want. I'm just going to say vector 3. So it's going to return a pointer to a vector 3, and I'm going to call it borrow vector 3, right? So this is kind of like my malloc. For right now, let's just return null. That's what it's going to return if there are no more objects available. We'll eventually get to making this actually do something useful. But before we get to that, our other function is going to be called return. So let's say return vector 3. And again, you can name this whatever you want. So let's, and let's just, good practice. Let's add void there, okay? And this one is not going to be void. This is going to be vector 3 pointer, and let's just call this v. Okay, so this is the thing that we're returning. Okay, so this is going to look a lot like malloc and free. We're basically going to say, hey, I want a vector 3 I want to be able to use, and then when I'm done, I will go through and I will free it or release it or return it. So I'm borrowing it and I'm returning it. Okay, so this provides the basic structure of our object pool, right? We've got a number of objects, we have an array of those objects, and of course, you'll see people use other things like hash tables and other structures as the backing. But the idea is you have a set of objects and then some way for your code to check out an object and return that object when it's done. And at this point, really, we're just missing one big thing, and that is we need a way to keep track of which objects are currently in use. And this could be done, and it has been done in many different ways. And those different ways can vary in complexity and speed and space efficiency and things like that. Today, I'm going to go with simple and conceptually easy to understand. So there are definitely fancier, faster, and more space efficient options out there. As always, let me know down in the comments if you would like me to explore some of those in a future video. But a first thing we could try, like we could come up here and I could say, for example, if we're just spitballing here, is I could come up here and add a member to my vector struct, and let's call it like allocated. and this could basically store whether this object is allocated or not. Now, I don't love this because the user might accidentally in their code, let's say that they use like memset to zero out this vector that they've just received, and in doing so, they just clobber this variable. So this is basically just asking for code to accidentally screw up my object pool's behavior. So I'm not going to do this. That is not going to be helpful. I could also keep a separate array, like I could do something like pool allocated, and then, so I keep this separate object here where each element of this array actually corresponds to the allocated status of each object in my object pool. That could work. I think having two different arrays is a little bit ugly. So for today, what I'm going to do is try to keep my object pool as much as a single cohesive thing as I can. So what I'm going to do is come up here and make a new struct. So let's make a new struct. I am going to call this struct pool object. And then really what I'm going to do here is say, let's make a Boolean, which is allocated. So it's this is a hybrid of these two different ideas. And then a vector3, which is the actual object, right? So this is just a wrapper around vector3 that adds an extra member here, this allocated member that keeps track of whether the thing is allocated or not. And then we come down here, and rather than say vector3 here, I'm just going to change this to pool object. Okay, so now we've got this array of pool objects where each pool object has a vector3, which is the thing I'm actually going to hand back to the user when they want to borrow it. And the advantage of structuring it this way is that now my user, when I'm just giving them this vector3 object, they don't have direct access to this allocated member unless they decide to do something funky or buggy with memory addresses and pointer arithmetic. But let's just assume that they're not going to do that. Okay, so now that we have this in place, we have some way to keep track of who is allocated and who is not. Let's come down here and let's actually implement our functions, our helper functions. And so first, let's go to this borrow vector3. And for this, what I'm going to do is simply let's start simple and just go, let's make a for loop that's going to start at the beginning and go through the whole array. And yeah, so we're going to go from 0 to num objects minus 1. And then what we're going to say is if the ith element of the object pool, if it's allocated, is false. Okay, so if we are not allocated, if this is free, basically, if it's an available vector, then what we're going to do is take this object pool square bracket I, so the ith member of the object pool array, and we're going to set the allocated variable to true. And then we are simply going to return the address of this member, right? So object pool, so I, and we want to return the address of its object. Okay, so that's what we're doing. We're basically taking the object, this vector itself in there, and we are returning the address. Okay, and we're going to leave this return null down here because this is just in case all the objects are already borrowed. So if all of the objects, let's say that I thought I only needed 10, but I really try to use 20 or 15 or 30, well, this is going to start returning null and we're going to have a problem. But at least it's going to let us know that we couldn't get an object rather than returning something that we shouldn't have access to. That is one advantage. One thing I like about object pools is they often help us find bugs sooner or more quickly than we will with just a standard malloc or free implementation. Now, before we move on, I want to mention that some people, you're going to hear people say that object pools are faster than malloc and free. In this case, I don't think that's true, right? Because I have this for loop that's running through this array every time. This is not going to be particularly fast. It is going to depend on how you implement your object pool. And in this case, because I'm going for simplicity, all of this checking is going to slow things down, especially once we have lent out a bunch of objects. The more objects have been borrowed, the longer it's going to take to find a free one because we're going to have to go deeper and deeper into the array. For my purposes today, that's fine because I'm really just trying to help you understand what an object pool is. But of course, as always, let me know in the comments if you want to see more about making things faster. Okay, now let's jump down to return vector, and we're going to do something very similar here. Just at least to start out with, we're going to make a for loop. Now, why do I have a for loop here? Well, I've got a pointer at the address of this vector, but I don't necessarily know which object I am needing to free. So, and I'll show you a faster way to improve this, but let's start conceptually again. Just keep it simple. My goal here is to not lose anyone while I'm implementing this. So let's first, we're going through basically our whole array and saying if our ith element of our object pool .obj, if the address of that is equal to the thing we are trying to release, right? So if this is the object that we're trying to return, then we are going to set the ith member of the object pool. We're going to set its allocated member to be false. And then we are going to return, because once we've done that, we know we're done. I'm also just as a sanity check here, just to make sure, because often I'm trying to make sure I catch any bugs early on. Let's add a sanity check, just a little assertion here that checks to make sure that the ith member of the object pool is in fact allocated. So this basically is serving the purpose of catching the case. Let's say I want to return a vector that I didn't actually borrow, right? It's not borrowed. That tells me there's probably a bug, and there's certainly a bug. So this is going to raise an assertion failed error, and we can debug it early on rather than letting it just hang out in our code until it causes some really frustrating condition. And then I'm also going to come down here because we should always, like, you shouldn't be returning something that wasn't borrowed. So down here, you should also, let's just add an assert false here. So if we get to the end of this and we didn't actually return anything, then I'm just gonna yell and say, hey, there's a problem here. This is not good. Because this case right here, if you reach here, you know, this is a bug. Look into it. Okay, now, as I mentioned before, this is also not the fastest way to do this. You know, we're basically every time gonna go through this array trying to find the thing that we're actually returning. We will make this one a little bit faster in a second, but for now it's good enough to test out, and hopefully it's clear what I'm doing. But before we can test it out, we need to jump down here and let's just replace this. So instead of having malloc, we're just gonna come down here and change this to borrow vector3. We don't need a size because we know the size of a vector3. It's always the same. And then down here, we are going to return vector3 and we should be good. Okay, let's just remove our malloc up there. So now we have a implementation that hopefully, as long as I didn't make any silly typos, should work. I have a makefile right here, very simple one. Please check out my other make related videos if you've never seen makefiles. But yeah, this is just going to compile our code for us. So then if we come down here and compile it, and so you can see that it works. It does in fact borrow 5 vectors here. Let's make it a little more readable here. I'm going to add the number, the index. Okay, so you can see basically we're allocating these. Notice that the address is always the same every time. The reason for that is simple. It's that we're always using the first one because we borrow it and then we return it. And so you always find the first one every time you ask for it. Just to illustrate this, let's come down here and let's actually borrow 2 at a time. Let's say you have some code that needs, you know, we have vector1 and vector2, and it's going to do something with each of these vectors. And then let's just print out both of them. So let's say we're going to get 2 addresses here and make this v1 and v2, resize this a bit, and then we'll just release both of them or return both of them. Okay, so now you can see if we run this, compile it and run it again. So now we're still able to get all of the objects we need. We're using twice the number of vectors. Again, notice that the addresses are always the same. It's always the first 2, the first and the second one. We're always going to get the same addresses over and over again. And also I want to point out that just like with malloc and free, we can still end up with memory leaks. Like, let's say that I came down here and I just forgot to return one of these vectors. So I'm borrowing 2, I'm just returning the first one. Now I have a memory leak. Now if we come back in and recompile it and rerun it, well, now if you look up here at the top, we are getting different vectors every time, and we always get the same first one because we're like, we find that one because it got returned properly, but the second one changes every time. And that's because we're leaving one of them in this allocated state. And so we just keep using the next one until you get to the end, and then all of a sudden we start getting null returned because we're running out of vectors. So you try to borrow a vector and it's just not available. So that's that, of course, but hopefully it helps you see what's going on. Okay, so now we do have a working object pool, but it is just a tad slow. And so maybe the last thing we can do is to make one of these functions a bit faster. In my opinion, the most egregious slowdown is this return vector3. And that is because there is really no good reason that we should have to go through this entire for loop. We should not have to go through the entire object pool to find the thing that we want to return. I mean, we have the address of the object right here. We just don't have its index into the array, and we can do a little math and make this for loop go away, make it basically completely unnecessary. So what I'm going to do, let's come down here and let's make a different version of return. That way, if anyone is checking out this code, you can get the code through Patreon as always. That way anyone going through can basically see this version. I'll just leave it here. We're going to mess around with this one. Now, in order to figure the math out, let's first think about how things are laid out in memory. So we have our array of objects, this object pool array. And now the object we're returning is a member of one of these objects. So it's going to look something like this. And I want to figure out, given the address, the memory address of that object, I want to figure out what index it is in the array. Basically, what member, what index in the array this belongs to. So what I want to do here is, rather than have this for loop, and let's just remove this as well. So I'm just going to trim out, because we still wanted to have this sanity check to make sure that things are allocated, and then we're eventually going to return it in the same way. But let's compute the distance in memory. So I want to have an unsigned int that's going to be I, that's going to be the index into my array. And how I'm going to compute this is pretty simple. I'm basically, really what I want to think conceptually is I want to take this vector that I'm returning, this object, right? And I want to take its address. I want to get the difference between this address and the beginning of my object pool. Okay, how far into the object pool in bytes am I? Now, of course, some of you are screaming, this is not how pointer arithmetic works. Correct. If I do it this way with just subtracting 2 pointers, I am probably going to get, well, suboptimal results. So what I recommend anytime you're doing math with addresses is we have a integer type called uintptrt. That is an unsigned integer that is the size of a pointer. And so I'm going to cast both of these things to uintptrts, and we'll subtract them. Now we should actually get the distance in bytes between these two things. So the beginning of the array and where my little object that I'm returning is actually located. And then, because I know the size of each of these pool objects, I'm just going to divide this by the size of pool object. Okay, so what this is saying is, yeah, I've got it in bytes, but how many bytes per pool object? So dividing this. And if you think about this in terms of real numbers, this is going to give you something like, 2.1, 2.2, whatever. But because it's integer math, it's basically just going to drop off the decimal, the part after the decimal, and we will just get the integer value that is the index in the array. So this will give me the index in the array. The only other thing, because I'm a little nervous about this maybe, the only other thing I'm going to do is just check to make sure that the address of the ith element of my object pool. So I just want to check to make sure that the thing I computed actually is the object that we're trying to return. Okay, so this is like, we did some math, that's great, but let's just say that I got the math wrong, or I've got some corner case that I haven't thought through. I'm sure if I did make a mistake here, some of you will point it out in the comments. But the idea here is that this assert should at least warn me and say, hey, you computed something that isn't the thing that we're actually trying to return. So maybe go fix that. But then once we have this I, then basically the rest of this is exactly the same. And now we don't have a for loop, so we're not hunting through. We just did some clever math, and now we don't have to hunt through our array. Also note that if you are using these uintptr_ts, those are defined up here in a header file, which is called stdint.h. So if you're getting errors that say like uintptr_t doesn't exist, you might need to add this include file, this header file right here. So this should work. Just to make sure, let's come down here and make sure that we can compile it. Great. And if we run it, you basically get the exact same thing we got before, only it should be quite a bit faster now, especially if we throw code in here that's going to borrow many, many objects. As you start to get more objects, this is going to get faster and faster. Well, I guess it stays the same, it just doesn't get slower and slower. Of course, we're still running out of objects down here at the end because I still left my memory leak in here. If we remove that, then you'll see that now we're back to that original behavior where we're just using the first two. So that's a quick look at object pools. Let me know down in the comments if you have other questions about optimizations, about object pools, or other memory related questions, or really any questions. Just let me know what you'd like to see in future videos. I hope you learned something new today. Please consider liking the video or subscribing to the channel to tell the algorithm you want to see more of this, and I'll see you later.